This is SpaceTime Series 19, Episode 81, for broadcast on the 16th of November 2016. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, Rosetta's Comet 67P much younger than previously thought, solving one of the great mysteries of globular clusters, and have scientists found a new way to bypass the Second Law of Thermodynamics? All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Rosetta's Comet 67P Churyumov-Gerasimenko may only be 1 billion years old. That's billions of years younger than previously thought. The new findings, reported in the journal Astronomy and Astrophysics, are based on simulations of how the two lobes which form the comet first came together and remain connected. Comets are primordial bodies formed out of the builder's rubble left over from the solar system's formation 4.6 billion years ago. But while they're primordial, comets aren't always pristine. Over billions of years, some comets will collide with or be impacted by other objects. Others will orbit towards the inner solar system, where the heat and radiation from the sun will cook up their chemicals, changing their composition. Using data from the European Space Agency's Rosetta spacecraft, scientists have studied Comet 67P in detail, discovering that the comet's actually composed of two separate comets, which merged together sometime in the past to form the celestial body we see today. The smaller comet forms the comet's smaller lobe, while the larger one forms its larger lobe. ESA scientists claiming the resulting double-lobed comet looks a little bit like a rubber duck. Computer simulations undertaken by research teams led by the University of Bonn concluded that the merging point or neck between the two lobes is fragile and wouldn't have survived the violent conditions of the early solar system billions of years ago when events such as the Late Heavy Bombardment were underway. The Late Heavy Bombardment occurred between approximately 4.1 and 3.8 billion years ago, when a disproportionately large number of asteroids are theorized to have collided with the early terrestrial planets of the inner solar system, including Mercury, Venus, Earth and Mars. The event, possibly a result of planetary migration by Jupiter and Saturn, occurred well after the terrestrial planets, including the Earth, had already formed and accreted most of their mass. That planetary migration event is also thought to have affected bodies in the outer solar system. The Bonn research team calculated just how much energy would be required to destroy a structure like Comet 67P in a collision. The computer simulation showed that the region connecting the two lobes is a weak point which could easily be destroyed, even with very low energy collisions. The new study also confirmed that the two lobes have each experienced a significant number of collisions over time, any number of which would have been powerful enough to destroy the structure connecting the two lobes. The authors say the computations mean Comet 67P's current shape isn't primordial, but probably only evolved in the last billion years or so, during a time when the solar system has become far less violent. The team also examined how the two lobes would have merged together in the first place. In their computer models, they had small objects with a diameter of between, say, 200 and 400 metres crashing into a roughly 5 kilometre wide rotating body shaped like a rugby football. The impact speed was in a range of between 2 and 300 metres per second, which clearly exceeds the 1 metre per second escape velocity for objects of this size. However, the energy involved still far below that needed for a catastrophic impact in which a large part of the body is pulverised. As a result, the target was torn in two parts, which, due to the effects of their mutual gravitational force, later merged into the two-lobed structure we see today. The computer simulation showed that the relatively small impact energy does not heat or compress the comet globally, allowing it to remain porous and retain its volatile material. The findings mean that while comets may well consist of their original 4.6 billion-year-old building blocks, those same building blocks no longer have their original form. A new study has finally resolved where the material needed to make new generations of stars in globular clusters comes from. Because the stars in a globular cluster were all originally formed from the same material, mystery has surrounded exactly how new generations of these stars are made. Globular clusters are tightly bound spheres containing around 1 million stars, which were all formed out of the same molecular gas and dust cloud. Because the stars in a globular cluster were all originally formed from the same molecular clouds, and so originally differ only in their mass, astronomers have been able to use globular clusters to study stellar evolution, the life cycle of a star. As the ages of globular clusters are thought to be very close to the age of the universe itself, they're considered to be veritable astronomical fossils because they retain a lot of information about the chemical composition and the evolution of galaxies from the epoch of their origin. In these clusters, stars of different sizes are formed, and so by observing the most massive stars which still survive, astronomers can work out the overall age of the cluster itself. Originally, astronomers thought that all the stars in a globular cluster were born at the same time. However, over the last 20 years or so, scientists have identified different generations of stars in a single cluster. But the origins of these successive generations was unclear until now. Astronomers have long known that stars of different masses die at different rates. Bigger stars tend to burn through their nuclear fuel supplies quicker than smaller stars. For example, while a relatively small yellow dwarf star like our Sun may live for 12 billion years, far more massive blue stars are sort of like the James Deans of the universe, living fast and dying young. In fact, massive blue stars burn through their fuel so fast they may only live for 1 million years, while tiny low-mass red dwarf stars are expected to live for literally trillions of years. In fact, astronomers are pretty sure that no red dwarf star has ever died of old age, at least not yet. When stars do die, their remains are spread through the interstellar medium, where they're recycled into new generations of stars. Now, a new study reported in the astrophysical journal Letters has finally resolved where the material needed to make these new generations of stars in globular clusters in the early universe comes from. The authors found the key are the most massive evolved asymptotic giant branch or AGB stars. This is the first evidence that these stars play a fundamental role in the contamination of the interstellar medium from which successive generations of stars are formed. The AGB, or asymptotic giant branch, is a region of the stellar spectral diagram known as the Hertzsprung-Russell or HR diagram, which is populated by evolved cool luminous giant red stars. This is a period of stellar evolution for low to intermediate mass stars after they've left the main sequence. By low to intermediate mass stars, we mean stars between about 0.6 and 10 times the mass of our Sun. The main sequence is the part of the HR diagram where stars are fusing hydrogen in their cores, the process which makes stars like our Sun shine. Observationally, an AGB star will appear as a bright red giant with a luminosity thousands of times greater than the Sun. The evolution of an AGB star begins with the star exhausting its supply of hydrogen through nuclear fusion in its core. The core then contracts, causing temperatures and pressures to increase dramatically. At the same time, the outer layers of the star, its gaseous envelope, are now further away from all that heat and gravity at the core. This allows the outer layers to cool and expand, turning the star into a red giant. Astronomers describe a star at this stage of its evolution as being on the red giant branch of the HR diagram. Eventually, once temperatures and pressures in the stellar core reach about 3 by 10 to the 8 Kelvin, helium fusion begins, halting the star's cooling and dramatically increasing its luminosity. Once the helium in the stellar core is exhausted, the star begins cooling and expanding again. Its luminosity then increases even further. The process is similar to what occurred when hydrogen fusion ceased earlier and the star first became a red giant. It's that similarity which led to stars at this stage of their evolution being called asymptotic giant branch stars. The interior structure of an AGB star is characterized by a central largely inert core of carbon and oxygen. That's surrounded by one shell where helium is undergoing fusion to form carbon, known as helium burning, and another shell which is undergoing hydrogen burning, where hydrogen is fusing to form helium. AGB stars have an expansive bloated envelope of gas and plasma, similar in composition to but less dense than stars still on the main sequence. The importance of AGB stars in globular clusters wasn't fully understood until this study. Various types of stars have been proposed as candidates, including supermassive stars, rapidly rotating massive stars, massive interacting binary stars, and massive AGB stars. But the mystery was determining exactly which stars were responsible for this phenomenon. The authors of the paper suspected the most massive AGB stars, which have between 4 and 8 times the mass of the Sun. To find out, astronomers used observations of the abundances of two elements in stars, magnesium and aluminium. They observed these through stars in the Sloan Digital Sky Survey and through the Apache Point Observatory Galactic Evolution Experiment, or Apogee Survey. The data was then combined with theoretical models of nuclear synthesis in AGB stars. In the first generation of globular cluster stars, the chemical abundances, for example those elements such as aluminium and magnesium, showed the composition of the original interstellar, or more accurately, intracluster medium, the gas between the stars and the cluster. However, over a relatively short period of time, a mere 500 million years, which is just the blink of an eye in cosmic terms, the intracluster medium is contaminated with the processed remains of some of the big original stars that have already died. That contamination then enriches the second generation of stars to be formed. Researchers think that some of the most massive stars in the first generation produce and destroy the heavy elements in their interiors through nuclear synthesis, and by rapid mass loss then contaminate the interstellar medium, where the second generation of stars later forms with different chemical abundances. The results reproduced for the first time an anti-correlation between the two elements in 5 globular clusters with very different metallicities. And to explain that jargon we just used, anti-correlation refers to a relation in which one quantity grows while another decreases, in this case aluminium and magnesium. The other term, metallicities, are what astronomers use to refer to any elements other than hydrogen and helium which a star contains. The production of aluminium and the destruction of magnesium in the interiors of stars is very sensitive to their temperature and overall metallicity, and so they offer a great diagnostic tool to unveil the nature of the contaminating stars. The higher the temperature in the zone where these elements originate, namely the base of the convection zone inside a star, the more aluminium is produced and the more magnesium is being destroyed. It's also known that the overall temperature in these zones rises when the total quantity of metals in the star falls. In massive AGB stars, different types of these anti-correlations are expected. At very low metallicity, scientists expect to find more aluminium and more destruction of magnesium, while at high metallicity the exact opposite occurs. The authors observed these exact variations in the anti-correlations of the stars in globular clusters, matching the theoretical predictions for massive AGB stars which produce these elements in their interiors and then eject them into space during a phase of extremely rapid mass loss. This research, therefore, finally ends the debate about which stars cause this process, and it resolves one of the outstanding unknowns in the formation and evolution of globular clusters. The next step will be the systematic analysis of all globular clusters seen in the Northern Hemisphere, which have already been observed as part of the Apogee project, as well as the large numbers of these systems which will soon be observed in the Southern Hemisphere as part of the Apogee 2 project. Scientists may have found a new way to circumvent the Second Law of Thermodynamics, one of the bedrocks on which modern theoretical physics is based. It's one of a handful of laws about which physicists seem to feel the most certain about. So much so that it's commonly believed in the scientific community that if someone has a hypothesis that violates the Second Law of Thermodynamics, then without question that hypothesis has got to be wrong. The Second Law of Thermodynamics states that in all energy exchanges, if no energy enters or leaves the system, the potential energy of the state will always be less than that of the initial state. In other words, entropy of a closed system always increases. By the way, entropy simply means disorder. You can think of it as a teenager's bedroom. No matter how clean it is at the start, the room will always end up looking like a crime scene at the end. In other words, it says things fall apart, and this order overcomes everything eventually. The second law of thermodynamics is underpinned by H theorem, which tells us that if you connect two substances, one hot and the other cold, they'll eventually settle into a lukewarm equilibrium. The hot substance can never end up getting hotter. It even has its own rhyme. You can't pass heat from a cooler to a hotter. You can try if you like, but you're far better notter. However, while science's understanding of quantum physics has advanced considerably, its understanding of the fundamental physical origins of the H theorem remain limited. Now, researchers with the US Department of Energy's Argonne National Laboratory think they've found a new loophole. The findings, published in the journal Nature Scientific Reports, demonstrates a situation where the second law is violated, at least on a microscopic level. Okay, so how did they do it? Well, the authors took quantum information theory, which is based on abstract mathematical systems, and applied it to condensed matter physics, a well-explored field with many known laws and experiments. They formulated just how the abstract mathematics of quantum H theorem related to things that could be physically observed. The work predicted certain conditions under which the H theorem might be violated, allowing entropy to actually decrease, at least in the short term. Back in 1867, physicist James Clerk Maxwell first described a hypothetical way to violate the second law of thermodynamics. He envisaged a small, theoretical being sitting in the door between two rooms. One room was hot, the other cold. And this little being only let through particles travelling at a certain speed. The theoretical creature was soon named Maxwell's demon. Although the violation's only on a local scale, the authors say the implications are far-reaching. It provides a platform for the practical realization of a quantum Maxwell's demon, which theoretically could make possible a local quantum perpetual motion machine. Needless to say, the authors are now trying to plan experiments to try and prove their concept. Of course, as we've been hinting, this isn't the first time the second law of thermodynamics has been violated. While the second law states that disorder in the universe can only increase with time, equations of classical and quantum mechanics do allow for time itself to be reversible. A few years ago, a tentative theoretical solution of this paradox, called fluctuation theorem, was proposed. Fluctuation theorem states that the chances of the second law being violated increases as the system in question gets smaller. This means that at human scales at least, the second law will always dominate. Machines will only ever run in one direction. However, when working at molecular scales and over extremely short timescales, things can take place in either direction. Back in 2002, I reported on SpaceTime's predecessor, ABC News Radio's Star Stuff, how scientists with the Australian National University demonstrated this principle experimentally, confirming that entropy could be reversed on very small scales. Their experiment, published in the journal Physical Review Letters, used lasers and 100 microscopic beads in a water-filled container. They fired a laser beam at one of the beads, electrically charging the tiny particle and trapping it. The container holding the beads was then rapidly shaken side to side 1,000 times a second, so that the trapped bead was first dragged one way, then the other. Researchers found that in such small systems, entropy can occasionally decrease rather than increase. However, they also found this effect was only seen if they examined the bead's behaviour for just 1/10 of a second. Any longer and the effect disappeared. The discovery has profound consequences and widespread implications for nanotechnology. It may help scientists better understand the behaviour of DNA in proteins, molecules that form the basis of life and whose actions can't be fully explained in some circumstances. But it also implies that tiny molecular machines may not work as expected. In fact, on very small scales of space and time, such machines may run backwards and be difficult to control. An Atlas V rocket is blasted into orbit from Space Launch Complex 3 at the Vandenberg Air Force Base in California, carrying the WorldView 4 high-resolution satellite.
Status check. Go Atlas. Go Centaur. Go WorldView 4.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We have RD-180 ignition, and we have liftoff of the United Launch Alliance Atlas V rocket carrying WorldView 4 for Digital Globe, doubling the capacity of the world's highest resolution imaging satellite constellation and allowing everyone to see a better world.
Lost some data and now has resumed, currently completing the pitch yaw roll program.
You're hearing the voice of Marty Malinowski providing launch vehicle ascent data.
Now flying the zero angle back phase of flight. RD-180 Performance looks very good at this point. Mach 1 up on maximum dynamic pressure. Now have passed max Q. RD-180 performance continues to look good. Body rates are controlling down the middle. Booster has throttled back, right on schedule. Signatures look good. Current altitude is 11, copy that as 13 miles. Downrange distance 5.3 miles. Current velocity 1,659 miles per hour. RD-180 continues to perform well. Injector pressures look good, as well as M2 pump speed. LH2 tank vent is underway. Have begun Q-alpha limited steering at this point, and the vehicle is now 50% of its liftoff weight. 80 continues to perform well. Coming RCS pyro valve. Pyro valve has now fired. System is pressurizing to flight levels, and signatures look good. Current altitude is 31 miles. Downrange distance 35 miles. Current velocity 3,760 miles per hour. And we've completed the Q-alpha limited steering at this point. Body rates continue to look good. Booster engine continues to perform well. Pump speeds, injector pressure, it's all on band. Booster is now 1/4 of its liftoff weight. Booster has begun to throttle to maintain 5 Gs. Constant acceleration. Space cooldown is underway. Now begun throttling to 4.6 Gs in preparation for BECO. Boost phase cooldown is complete. And we have engine shutdown. BECO looks good. Have indication of a clean stage separation. Box and fuel restart on the RL-10. And 2 purge firing. The RCS is underway. Have ignition and full thrust on the RL-10. Up on payload frame jettison. And have indication of a clean jettison.
This is Atlas Mission Control at T plus 5 minutes, 28 seconds. We've just seen the successful liftoff of the Atlas V rocket carrying Worldview 4 for Digital Globe. All systems continue to operate nominally. Our next event, cutoff of the Centaur engine, is scheduled to take place in approximately 11 minutes.
The flight had been delayed since September. The mission was first scrubbed due to a liquid hydrogen fuel leak, which caused an ice ball to form on an umbilical connecting cable. Then the mission was delayed again, this time by large wildfires which ravaged the area in September. On board the United Launch Alliance Atlas V was Digital Globe's Worldview 4 multispectral commercial imaging satellite. The Atlas V's first stage is equipped with a single RD-180 twin-chambered rocket engine. It burns a highly refined form of kerosene jet fuel called RP1 with liquid oxygen. The first stage burns for approximately 4 minutes and 3 seconds until main engine cutoff, or MECO, and main stage separation. The Russian-built RD-180 is based on the RD-170 engines originally developed for the Zenit rocket. Once the first stage has been jettisoned, the Centaur upper stage Aerojet Rocketdyne RL-10C1 engine fires up. This engine, burning liquid hydrogen and liquid oxygen, then carries the Worldview 4 satellite into a 617-kilometre high sun-synchronous orbit. The 2,087-kilogram satellite is based on Lockheed Martin's LM900 bus, with an LMX avionics package and a 7-year design lifespan, although theoretically it may well remain operational for up to 12 years. Lockheed Martin originally built the satellite as the GeoEye-2, but then renamed it Worldview 4 following the merging of GeoEye and Digital Globe. Worldview 4 is equipped with panchromatic and multispectral imaging systems with a 13.1 kilometre wide coverage. The panchromatic imager has a resolution of 31 centimetres, while the multispectral imager has a 1.24 metre resolution and can sample the blue band at wavelengths of 450 to 510 nanometres, green between 510 and 580 nanometres, red between 655 and 690 nanometres, and infrared between 780 and 920 nanometres. The new satellite joins Digital Globe's 4 other satellites, Worldviews 1, 2 and 3 and GeoEye-1, allowing the company to image any location on Earth an average of about 4.5 times a day. Following separation of the Worldview 4 main payload, the Centaur upper stage continued for another orbit before deploying 7 smaller CubeSat satellites as part of the National Reconnaissance Office Enterprise mission. Among the CubeSats to be deployed were Aerospace Corporation's AeroCubes 8C and 8D. These are 1.5 unit CubeSats which are part of the IMPACT mission, testing several technology demonstration experiments, including a new type of ion propulsion system, as well as new types of solar array materials and materials research using carbon nanotubes for radiation shielding. AeroCubes 8C and 8D followed the earlier 8A and 8B satellites, which were launched aboard a US Air Force X-37B spaceplane last May. Also released aboard this month's Atlas V launch was the US Air Force's 1 kilogram CELTI CubeSat, designed to spend 6 months in orbit testing a new enhanced location transponder. Another satellite to be launched in orbit was the U2U 2-unit CubeSat, which is undertaking an electron and globe star mapping experiment. The Prometheus 2A and 2B 1.5 unit CubeSats developed by the Los Alamos National Laboratory were then deployed to test how well small satellites can relay video, voice and data transmissions. Prometheus 2A and 2B are the first of a new second generation of Prometheus constellation satellites. They follow on from 8 first-generation satellites launched back in 2013 on a Minotaur 1 rocket. Additional Prometheus second-generation CubeSats are slated to be launched on the first flight of SpaceX's new Falcon Heavy launch vehicle, which is now expected to fly in 2017. The final CubeSat payload aboard the Atlas V was the Johns Hopkins University's 5-kilogram Raven 3-unit CubeSat, which will spend 6 months in orbit using carbon nanotubes to collect the total radiation output emitted or reflected by the Earth. This will allow scientists to compare the Earth's total radiation output with that from the Sun to see how much solar radiation the Earth retains. This mission was the 6th flight this year for the Atlas V rocket and the 9th launch this year for the United Launch Alliance, which has also flown 3 Delta IV vehicles. The United Launch Alliance's next flight will be the launch of the joint NASA-NOAA GOES-R Earth observation satellite, slated for liftoff from Space Launch Complex 41 at the Cape Canaveral Air Force Station in Florida on November 19. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from SpaceTimeWithStuartGary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter, and Tumblr. Just search for SpaceTime with Stuart Gary.